So today we'll be studying the Newton's method for root finding in one dimensional. Uh, so let's begin. So let us consider this graph where on the x-axis you have x and on the y-axis you have f of x. And yeah, and let's say the function looks something like this. Or maybe let's make it more complicated, something like that. And according to the definition, the x star would be right here, where the value of the function is 0. And let's say we start with an initial value of x, which could be, let's say here. Let's call it n. We are in the nth iteration. Okay, so we will be making some approximations. So let's first draw the tangent line at that x. Okay, now you can see that this tangent line is actually intersecting the x-axis at this point, and we know that this point is where the value of the function or value of the line is 0. So let's find out the slope for that line. So we know that the slope is the derivative of the function at that point, and we know how to compute the slope of a line. You subtract the y values at these 2 points. So you take this point and you take this point, and you construct the slope from these 2 points. So at the top we will be subtracting the y values. So let's take this point to be the initial value, the first point. So it could be y, and this should be the value of the function. Okay, let's say this point is where we want to move next. Why? We'll get to that later. So the x value, let's call it the next value, minus the x value here. So if we set this value as 0, and if we move the things around, we can say that xn plus 1 is equals to xn minus f of xn over f prime xn. So what is this? This is the better guess that we have made uh, to x star. So we think that xn plus 1 is going to be better than xn at approximating the value for x for which the function's value is 0. So let's get the corresponding xn plus 1 value. So the corresponding xn plus value would be right here. So this value corresponds to xn. So what if we repeated the same process that we did for xn, and find, sorry, this is n plus 1, and we find the next better guess. So let me draw the tangent once again at this new point. So as you can see, the tangent, this was steeper, and this is now not so steep. So as we can see, like the further away from the function we were, the more fast we were reaching the root of the function. So if we repeat the process again, which means we get the another y is equals to 0 value, which is right here, and we find the corresponding x value. So it's going to be xn plus 2. So as you can see, xn plus 2 is closer to x star than xn plus 1. So we have the new xn value right here, and again we're going to draw the tangent at that point. So as you can see, we have arrived here, which is going to be xn plus 3. So with every successive step, we can see that we are getting closer and closer to x star. So after a few iterations, we will be very close to x star. So let's say we have made k iterations. So let's start from 0. So we have made k iterations, and we have reached x star. So if we calculate the absolute difference between them, that has to be less than some epsilon value, which is which could be your tolerance. So this says that uh, this this implies that k iterations are needed to converge to x star with desired accuracy. Okay, now let's move on to the coding section. Hi, welcome to the coding part of Newton method for root finding for one-dimensional functions. So let's begin with some functions that I already have here. So this is the function that we have, 5x cubed plus 4x squared minus 8x plus 8. And I've also computed the first derivative of the function. Now let's try to plot the function here. So I'm going to be using NumPy, and I'm also going to be using Matplotlib for plotting. So now we're going to create some sample data. So let's say x's is equals to np dot linspace from let's say minus 10 to 10, and we want 100 points in between. And let's compute the corresponding y values here. Just f on x's. Okay, now we have computed this. Now we're going to be using matplotlib to plot this. I'm just gonna create a figure first. So let's just say 8 by 5 and plt dot plot x's y's and plt dot show. That's gonna plot the function for us. As you can see, for minus 10 we're getting as low values as minus 4000, and for 10 we're getting as high values as 4000. Now, from this, we can see that there is actually a root somewhere for which the value of the function is 0. So let me also draw the horizontal line, uh, x line, h lines, yeah. And I'm just going to say that the value of y is going to be just 1. Oh, sorry, 0 for minus 10 and 10. Let me color this something else. Color is equals to red. So yeah, it is intersecting somewhere. So let me try to squeeze the x range a little bit. So let's say I'm going to go from minus 2.5 to 2.5, and I'm also going to change the range here for x min and x max. So yeah, as we can see, the root of the function is somewhere over here, and now we're going to be using the Newton method to find the root. So let's say I'm going to start with x is equals to 0. I'm going to say that the value of the function is going to be uh, is going to be 0 at that point. That's just a guess. Now what I'm going to do is I'm going to start a while loop, and I'm going to let it run indefinitely. And I'm also going to use a flag variable to check whether it is converged or not. And then let's evaluate the function at the x value here, and I'm going to compute the next value, xn plus 1 value is equals to x minus f of x over f prime of x, which is what we discussed in the previous discussion. Now let's also compute the next function value, f let's just say f of x next. Okay, now I'm also going to check if the next f is I'm going to check the absolute value of this, else this loop might run indefinitely if the absolute value of the function is less than an epsilon value, which is what we discussed here. Then if that's the case, we're going to break the loop. So let's define the epsilon value here. I'm going to say that it is 1e minus 6. And now I'm also going to use a counter variable to check how many iterations it took for the Newton method to converge. I is equals to I plus 1. And I'm also going to set the uh, current value of x to the x next, which is x equals to x next. Okay, so I'm gonna let it run, and I'm going to use a while else, which means that no, that a while else would not work here. We'll talk about that later. Okay, so let us look at the value of x now. So it ran, and it ran up to some point, and we can see that it has given us a value of x somewhere close to -2. And we can also see that on the graph right here that the function value is actually 0 at somewhere around -2. And now let's also compute the value of the function at the x we've gotten. So as you can see, this is a very small value, which is I guess smaller than 1e minus 6. So I think, yeah, we have actually converged. So yeah, actually we are supposed to use x next here to check. So next. Okay, let's check the value of function at x next. So yeah, this is e minus 11, so which is very small value. So yeah, that's it. That was Newton method for one-dimensional functions.